All right, our next group presentation is Mr. Logan. Good afternoon, everyone. As many of you may know, my name is Logan Scully. I'm part of Group 3, and this coming week we will be doing the gas turbine jet engine experiment, also known as Experiment 5. So the objective of the experiment is to gain an understanding of the turbogen gas turbine system as a whole, to understand how to operate it, understand how it works, perform calculations, and determine the optimal operational settings. So a quick overview of the lab itself. In this one lab, there's 5 sessions. They're like 5 experiments. So they are the overview and operation. We're going to do turbogen data run plots, system analysis, engine performance analysis, and electrical generation analysis. So the thermodynamic principles included are the first law, which is for steady state and steady flow conditions. And with that, we know using the continuity equation that the mass in and out are equal to one another, so we're given the equation below. All right, so a brief real-world example. And today, this is a power plant, and power plants are the power generated through either steam, which is hydro, nuclear, or coal. And in this situation, it's a steam turbine, and it's called the base load generation. So in this diagram, we're given the electrical demand curve, and on any given good day, where it's like not possibly too hot, you would have energy needed would go to a certain point, and it would have a plateau, and at the end of the day, it would come down. But on days where we would needed a lot of electricity, possibly due to high temperatures, and we needed to run air conditioners, the curve, so it would go to the base position, and it couldn't run any higher. So that's when the gas turbine, called the peaker, because it finishes the peak, would pick up the slack, and it would go to the peak and then back down, at which point it would shut off, and the steam turbine would take back over. So the apparatus used are the turbogen, which is a picture of it here. This is a photo of what ours looks like. This is the jet engine, or the SR30 engine. On the components of this engine, we have an air intake, a compressor, the jet engine itself, the turbine, the thrust nozzle, the thrust transition deflector, the free turbine itself, the electrical alternator, and the load supply outlet. So to break that down, the way this works is air comes into the intake, and it is compressed and mixed with fuel. At that point, it is combusted in the combustion chamber, which produces thrust. That thrust is going to go through the thrust deflection nozzle here. At this point, another real-world example would be an aircraft. This is what would propel the aircraft, but in this situation, we're going to be using the thrust to create electrical power. So the thrust would go here and hit the thrust deflection nozzle, which is then going to hit this free turbine, and it's going to spin and produce power to the alternator, and from that point it will produce the electrical power, which can then be used for whatever it's needed for. This is also known as the the ideal cycle, which is the Brayton cycle. And in our case, in the real world example, these constant entropies would be shifted to the right. For our experiment, we will be using data collection, and these are the positions of the sensors. The sensors are going to be for pressure and temperature, and voltage and RPMs. So using that data acquisition system, this is the turbogen system, you're going to open the program and choose measurement and automation, and this is the dashboard that you would be given. At this point, you have temperature sensors and your pressure sensors up top, and at this point you would log the data to file, which is the second button from the top. I'm sorry if it's a little blurry. So when you're logging these pressures and temperatures, these are the graphs that are going to be produced in the experiment. At this point, you're going to be given a turbine. This is an example of a turbine inlet and outlet pressure graph. Sorry if it's a little bit blurry. This is what was given in the lab manual. This is the control panel that's going to be used. You have your on and off switch, your load levers. You have digital readouts, which will give you turbine temperature, engine speed, and turbine rotational speed, along with different pressures. So an overview of the procedure that we're going to be doing. In the first experiment or session, we'll be performing startup, pre-startup, startup operation, and then starting the data acquisition, which rolls over to the second session. At this point, we will graphically plot the data points that we were taking down and use those in the third session to perform the calculations for the steady state and steady flow conditions. At that point, we'll also continue using those charts for the performance calculation at the engine at the inlet and exit of the nozzles. And the final step is to calculate the optimal operational settings. So the relevant equations, we have specific work, specific energy, and also thermodynamic efficiency. Also included are air density calculations, velocity, the flow rate calculations for mass and volumetric flow, Mach number, and power-specific fuel consumption. So just to give an example of the predictions made, so we would use the graphs given, or the graphs that we produced from our data points, and choose a position on that graph. From that, we would be given our pressure and temperature, and from there we would take the pressure and temperature and go into our air charts. With the air charts, we would find our enthalpy, which is given in kilojoules per kilogram mole, and we would multiply that by the molecular mass of air to get a enthalpy value. And these are the values, as an example, at the different inlet and outlets. So here are more calculations, or calculations used with those enthalpy values. So we know the specific work at the compressor, which would be from stage 1 and 2, would be 146, the specific energy added by the fuel, the work of the turbine, and the power of the turbine cycle. These would all be used in the calculation of the thermodynamic efficiency, which is noted here. And for conclusion, some possibilities of error that I came up with would be possible uncalibrated temperature sensors, pressure sensors, and you could also miscalculate values due to pulling the wrong values from the air table and charts when you're working on your calculations. And that is all. Any questions?
So, any questions? If you go back 2 slides, 3 slides.
3 slides?
Yeah, 3 slides, 2 slides. You had the molecular weight of air. Yeah, you said something wrong here. Unless I misheard you.
I said wait, I'm in mass, I apologize.
Mass, but you also said something else.
Where?
Did I mishear it? Or did you say something wrong? What was it? You know? I thought you said you have to multiply those 2 things to show up somewhere else. You multiply something.
No, sir.
Did you say multiply something by molecular mass of air? No? No? Okay. You go from kilojoules to kilogram per mole.
And you divide
Why?
to get your, I apologize if I said multiply.
That's fine. And if you go back, like somewhere else. Oh yeah, no, next one. There you go. What is
Here.
no, Mach number? Your Mach number equation.
Yes.
What is CP?
Um,
Is it something new?
no, sir. I might have taken it down wrong.
There's no CP. At least that's what I know. Yes, there's nothing called CP. There's definitely CP.
Yeah.
Must be CP or CV. That's gamma.
Yeah, I must have, I think
It's a typo. That's a gamma. So GC, gamma, R, air, and time. Does that make sense? Is that the mass Mach number? So how do you define Mach number?
I don't remember right offhand.
Velocity divided by the speed of sound in that medium, right?
Yes, sir.
And is that speed of sound? R of air, T, G, C, gamma? Possibly. Okay. 8.1%, that sounds very low.
Yes, sir.
Do you think that's reasonable?
Sir?
Do you think that's reasonable? Do you think you expect your measurements next week to match up to 8.1%?
I hope it would be more efficient than that.
You think so? How many of you think it will be more than 8.1%? How many of you think it's less than 8.1%?
I don't know.
Less than 8.1%? Wow, man, you really have no faith in your
We're in the same.
Are you just saying that because, I'm asking a question? Are you guessing?
I'm guessing.
Well, what's the efficiency of your car? How about that? Let me ask you simply. What do you think your car is?
20%. It's very low.
Yeah, thermodynamic efficiency of your car. Now you got to be careful. Mechanical efficiencies will beat you up at the end of it,
Yeah.
right? So, what is thermodynamic heat efficiency? Not how much mileage you get in terms of driving your car, but just heat to work.
I know it's low, I'm not sure about it.